All right, so for today, we are starting the basically second to last thing in this unit. Okay? That said, work energy theorem is probably the most important concept there is in physics, any physics. Because without work, nothing happens. Without energy, nothing happens. Okay? In order for anything to move, okay, or anything like that, energy has to be present and work has to be done. Right? So work energy theorem is kind of the basis for anything to get accomplished. So the key points for today, we've got to understand the work energy theorem. Okay? Understand that work and energy can be equal, numerically equal, but one cannot exist without the other. Okay? And the reason that one cannot exist without the other is because of their definitions. And we actually talked about this on the first day of the unit. Okay? Work is defined as a change in energy. Okay? So anytime energy is changed, work is done. And we're talking mechanical energy here. Okay? So that would mean like if I lift something from the floor to a table. Right? That would be work, because I would be changing that object's gravitational potential energy. Because on the floor, it can't fall. But on the table, it could. So it has the potential to do work. Okay? Everyone follow me on that? If I pick something up and throw it, okay, then I'm changing its kinetic energy, because initially it wasn't moving and had no ability to do work. Okay? But as soon as I threw it, now I have a moving object. Okay? That hits something, it can do work on it. Right? So work is a change in energy, and energy is the ability to do work. So you can't have one without the other. It's very much a chicken and egg argument. Okay? I can't do work without energy, because work is a change in energy. But energy is the ability to do work, so I have to have it in the first place. Incidentally, which came first? I think we had this discussion, chickens or eggs? Chickens. Eggs. Yeah. Birds evolved from reptiles. Reptiles lay eggs. Therefore, eggs came first. Simple question. It's supposed to be some deep philosophical question, but it's totally not when you look at it from a science perspective. All right, so these are our kind of definitions of the things that we're going to work from. Okay, work is a change in energy. Anytime work is done, energy is changed. Now, in order to do work, what are some things that you might have to do? Let's look at this as a simple example. Okay, right now, does my chair have any energy? What about now? Why? I put, oops, sorry about that. Wow, those wheels are really good. What did I do to it? Okay, I put energy. How did someone said it. I pushed it. Okay, if I push it, I'm exerting a what? Starts with F. Force, yeah, okay? And I'm exerting that force through a distance. Okay? So the other way to calculate work is a change in energy. I could go final energy minus initial energy and calculate work. Or I might know the force that I used and the distance over which I used it. Okay? In that kind of easy example there, I pushed it pretty hard, but not over a very great distance, right? It was basically just extending my arms. Right? So the distance over which I exerted that small force was maybe 75 centimeters, okay, at the most. What if I exert that same force, but now I do it this way? Did I exert that same force over a greater distance? What did you notice about the movement of the chair? Yeah, and it would have gone all the way to the wall had I not chased it down and stopped it. Okay, so did I do more work that time? Same force, greater distance, more work. Okay, or I just exert a greater force over that smaller distance. I just push harder. Okay, if I push harder, I do more work. Okay, and if I do more work, I change the energy by a greater amount. Right? Everybody okay with that idea? It's fairly common sense, right? Like it's something you can kind of see and experience yourself. All right. We talked about these as well the first day, kinetic energy and potential energy. Okay? Potential energy is energy due to position, that's what we'll mostly be dealing with, or condition. Okay? Condition could be something like chemical energy, it could burn or explode, or it could be elastic. If something is stretched or has its shape changed and it wants to go back to its original shape, then it is holding elastic potential energy. We're mostly going to be dealing with gravitational potential energy in this unit. It simply means something can fall. Okay, so anything that's not sitting on the ground has gravitational potential energy. All right, and then we just talked about the relationship between force and work. Greater force, more work. Greater distance, more work. Okay, all right. So energy, just like anything else, okay, is kind of a measurable quantity. We can't really see energy, okay, but we can see the results of it. Okay, so specifically, energy is a measure of an object or system's capacity to do work. So that's the definition of energy, right? So for example, a brick held in your hand has the potential to do work on your toes if dropped. Okay? And then work is the transfer of energy from one object or system to another. So if you've ever played pool, okay? When one ball hits another ball, okay, we're taking energy from one and transferring it to another. All right, this mousetrap, does it have energy? No. Yes, it does. Okay, in this condition it does. Why? Right, it's loaded. Okay, I mean, and that's what you do to a mousetrap. You load it. Okay, how do you load it? Yeah, you pull it back, okay? Because these are the parts. I didn't name them. You take the killing bar, appropriately named. I mean, that is the part that does the killing, okay? And you pull it back like this. Well, the killing bar is attached to a spring, okay? And so when you pull it back, you're deforming the springs. Springs store elastic potential energy because if you stretch or compress them or change their shape in any way, they will hold that energy. Because when you compress or stretch a spring, you are exerting a force through a distance. I mean, think about it. If you just push on a spring and compress it, you exerted a force over whatever distance you shortened the spring. Similarly, if you stretch the spring. Okay? And if you do either one of those, the spring now has elastic potential energy because you've done work. Work's a transfer of energy. Okay? So when you load the mousetrap, okay, you have done work and given it potential energy. If the trigger, okay, that's this part where you put the cheese or peanut butter works really good, okay, if that trigger gets set off, okay, then all it does is release the trigger bar. Okay, so the trigger bar just goes right here onto the trigger. Okay, when you step on that or press it with your finger, don't press it with your finger. Okay, it'll release that, and then of course the spring will force the killing bar forward. Okay, now when the spring is forcing the killing bar forward, what is it doing? Work. Yeah, it's transferring energy, and it will do work on the little unfortunate creature that has triggered the mousetrap. Okay. Now, does it change? What does it change about the mouse? Does it make it go faster? No. Okay. Make it go higher? No. But it changes its shape. That's work. Okay, no, that's gruesome. I'm sorry, but okay, it's work. Okay. If you change the shape of something, okay, you have done work on it. If you dent something, you've done work on it. Okay, because you've exerted a force through whatever distance you dent the material. Okay, so any of that counts as work. It doesn't necessarily have to mean the object went faster or higher. Okay, it still counts as work. All right, everybody understand energy and work and how they're related? Okay. All right, so let's imagine something like a tennis swing. Okay, how many people have ever played tennis? Okay. All right, so in basically any racket sport works the same way. How fast you can hit the ball is dependent on two things. What are they? Don't overthink it.
Like your strength.
Your strength.
How fast it comes at you. How fast it comes at you.
Okay, let's say you're serving it, so you're just throwing it up in the air.
Okay.
So you're not returning something, because you're right, if I was returning something, that would play a part. Okay, so one thing is my strength. My strength influences how fast I can move the racket. Okay, what else?
The racket. Well,
Kind of.
What if you like the part of the racket? Because like if you hit it with like the top, then it's gonna like.
Yeah, you're absolutely right. You're on the right track. You're telling me the right things. Okay, my strength is related to the force I can exert through the racket. And then my technique / my equipment, the racket, influences this part, the distance. Okay? There's a couple of reasons why we use a racket and not a paddle in most racket sports. Okay? The first and most obvious one is weight. Okay? Having strings as opposed to a solid piece of material is much lighter, much less air resistant, okay, and all of that kind of stuff. But the other part of it is the strings are flexible. So when you hit a tennis ball, okay, so if I'm looking at the tennis racket from the side like this, okay, and I'm making that serve, the mesh, okay, the strings of the racket, they'll actually bend backwards behind the racket, and the ball will sit in here, okay, for a short period of time. But if it does that, the longer the period of time, or the greater the distance that it's in contact with the racket for, the more distance, thus the more work I can do, right? So not only is how strong I am going to influence how fast I can serve a tennis ball, but how well I hit it also influences that. As Alec was saying, if I hit it on the frame, it's going to be a terrible serve because the ball is going to just bounce off the frame. Okay? I'm only going to get to exert that force over a very small distance. But if it gets hung up in the net, okay, or the strings, and sits there, now I'm pushing that ball forward over a much greater distance before it flies off the face of the racket. Okay, does everyone kind of follow me there? Right? This is like all sports science. Okay? Anything that's, well, basically anything that you use to hit something else. Okay? This applies to hockey, same thing. Right? Back, when I was a kid, all hockey sticks were made out of the same material, wood. Okay? Wood's a little bit flexible, but not terribly flexible. So when you are taking a shot with an old wooden stick, the stick might bend ever so slightly. Okay? When you would get it on the ice and be pushing the puck with it. So it would bend a little bit, and it would conversely snap forwards, which meant the distance over which I could exert my force was about that much. Modern sticks are made out of composite materials. Okay? They are much, much more flexible. And so as a result, they increase the distance over which you can exert force, meaning you can shoot faster, further, faster, whatever, anything that has to do with the amount of work you can do on the puck. You can do more work on the puck, okay? Even if you're the same, like if you gave, a professional hockey player an old stick and a modern stick, they always shoot faster with the modern stick. Okay? Simple physics, because they can exert their force over a greater distance and do more work, okay? Now, there are going to be caveats to that. If anything happens to the composite stick, like it partially breaks or anything like that, then it loses that elastic effect and will be less effective than the wooden stick. But okay, there's a reason why basically nobody plays with a wooden stick anymore, okay? Because everybody shoots faster with these. Okay? Golf is another sport that's embraced that. Not so much in the clubs, but the ball. Okay? Back in the day, the golf ball was like hitting a rock. It was hard, inflexible. Okay? Now, golf balls are really soft. And so when they hit the face of the club, okay, so if this is your, let's say your driver, okay, so this is the hitting face here. When the ball hits the face of the club, okay, it smashes flat against the face of the club, okay, which means it stays on the face of the club for longer. allowing you to exert that force over a greater distance and thus hit the ball further. Okay? So basically the only sport that has not embraced sports science like this is baseball. They endorse a different type of sports science. There's a lot of that in a lot of sports, but baseball is the worst. Okay. And the other thing that they also do in baseball is they cork bats. Lots of cheating in baseball. Okay? I don't know if anyone ever saw that when Barry Bonds got caught. Okay? So what he did is he drilled out bat. Took a drill press and hollowed out his bat and corked it. Okay? So now the bat is
Hollow.
right. Can you swing it faster?
Yep.
Yeah. Problem is, bat's hollow. You're strong and on steroids, and you swing the bat and you make good contact with the ball, what's going to happen to the bat? Exactly why he got caught. Okay? Because the umpire went out to collect the pieces and went, this bat looks strange. Hollow in the middle. Bats aren't supposed to be hollow. They're supposed to be a chunk of tree. Okay? And it wasn't. So, sports science. Lighter bat, swing faster. Okay, is that making sense? So we're still back to this force and distance, force and distance. It's always about how much work can you do. Anything that can increase the amount of work you can do increases the energy that you will transfer, and thus the final energy of whatever you're doing work on. Okay. All right. Okay, so work, like we said, is related to the force that acts on the object. So if I'm shooting a bow and arrow, okay, the further back I can pull the bow, the greater the distance, okay, the more work would be done. The stronger I am, the more I can bend that bow, okay, the more work I will do on it, okay, and that will increase the amount of energy that the arrow will have when it leaves. Okay, in the perfect physical world, if I do 100 joules worth of work on the bow, drawing it back, and then I release it, how much energy will the arrow have when it leaves the bow? 100 joules. Okay, in the perfect physical world, if I deform the bow and do 100 joules worth of work, all 100 joules will be transferred to the bow or to the arrow. Sorry, when I release it. Okay, that's the world we're going to work in because it's much simpler. Okay? We're going to ignore, losses of energy like sound and heat and all that other stuff that actually happens in the real world, and do all of our stuff in the perfect physical world. Okay, and that's going to be the basis of all of our work energy theorem questions. Okay, if I exert a force over a distance, it will change the energy of the object. So in other words, if I'm looking at a bow and arrow system, okay, the force I exert on the bow multiplied by the distance I draw it back will equal the final kinetic energy of the arrow minus the initial kinetic energy of the arrow. Now, since the arrow is sitting in the bow, not moving, how much kinetic energy does it have before I let it go? None, right? Its velocity, its speed is 0, okay? So what we'd be looking at is the kinetic energy would be 0, so the work that I do will be the final energy of the arrow, exactly what we were talking about a minute ago. Okay? So that would mean force times distance equals kinetic energy. That's the formula for kinetic energy. We haven't really talked about that yet, but that's it. Okay? So, something's energy is related to its mass, something's kinetic energy, sorry, is related to its mass, how heavy it is, and how fast it's going. Okay? But what do you notice is on the speed here? Speed squared. Okay? So if I increase the speed, will that have the same effect as increasing the mass? The answer is partly yes, but also partly no. Okay? If I double the mass and I don't change the speed, I'll have twice as much energy, right? Because I'm multiplying by m. But if I double my speed, speed is squared. So if I double my speed, I'm actually making this not 2 times greater, but 4 times greater. Okay? When you double something and then square it, it's now 4 times larger. If I triple something and then square it, it's 9 times larger. Okay? So speed is exponentially related to energy. Okay? Now this is something they don't teach you in driver's ed, and I still don't understand why. But speed is exponentially related to energy. So if you go 60 kilometers an hour through a playground zone, why is that really, really bad?
It'll take you longer to slow down twice as long.
How much longer?
Twice as long as way.
Not twice, 4. Okay, if I double my speed, I quadruple the amount of energy I have, which means it'll take me not twice as long to stop, but 4 times. So instead of stopping in 10 meters, I stop in 40. That's a huge difference when a little kid runs out in the street in front of your car. Okay, here's the other thing to consider. Speed is exponentially related to your energy. If you have 4 times as much energy, how much more work can you do? Four times more. Remember what happened to the mouse in the mouse trap? Now it's a little kid in the street in front of your car. I'm actually a little distressed that you find that funny. Can you do a lot of damage to a little kid? Yeah. That's why the speed limit in a school zone or a playground zone is so slow. Because speed is exponentially related to energy. Okay? I'm going to show you, I'm going to prove it to you mathematically here. Okay, let's say that you're driving an average size car. Mass is 1,500 kilograms. Okay? The brakes in that car can exert, let's say, 7,500 newtons worth of force. Newtons are the units for force. Okay? So in order to stop you, they can exert 7,500 newtons worth of stopping force. Okay? You are going to be traveling the speed limit, 30 kilometers an hour, okay? Which is 8.3 meters per second. Right? So I'm going the speed limit, 30 kilometers an hour, which in meters per second is 8.3 meters per second. Okay? Work is a change in kinetic energy. In order for you to stop, your car has to do work on something. It's usually your brakes. Okay, so when you apply the brakes, okay, there's a shoe that pushes against the rotor, it makes friction, okay, and essentially the energy of your car does work on the brake pad and rotor, turning it into heat. Okay, the brakes get really hot when you apply them, and it turns your mechanical or kinetic energy into heat, and that's what brings you to a stop. Okay, everybody follow me there? So we just said that work is force times distance, and kinetic energy is 1/2 mv squared. When I stop, how much kinetic energy do I have? None, because v would be 0. Okay, so the amount of work that has to be done is equal to my kinetic energy the instant I apply the brakes. Okay, because then it's going to change after that. So this distance becomes my stopping distance. Okay, it's the distance over which my car is going to do work on my brakes and bring me to a stop. Everybody all right with that? Okay. So if I want to solve for how far it will take me to stop, what do I have to do with F? Divide it over to the other side, right? Just algebra, okay? Okay, so my stopping distance is going to be 1/2 times the mass of my car, 1,500 kilograms, times how fast I'm going, squared divided by the force my brakes can exert while stopping me. Okay, then I divide that by the force. So that's the amount of energy my car has. 51,667.5 joules worth of energy. That is a lot. Okay, divide that by the force my brakes can exert. It's going to take me 6.9 meters to stop. It's not too bad. Okay, that's if I'm going to speed limit. Okay, what if I go 60 kilometers an hour?
Roughly like 13.8-ish.
Is it twice as far?
Oh, 4 times as far.
4 times as far. Okay, so I'm just going to prove it to you mathematically here. All the same numbers, all I'm going to do is double this. Okay, just going to double my speed. 1/2 times 1500 times 16.6 squared divided by 7500. Everything else remains the same, only changing the speed. Okay, so we'll have our 0.5 times 1500 times now 16.6 squared divided by 7,500. Four times as far. Okay. Four times further. Now, I know none of you would ever drive through a school zone or playground zone at 60 kilometers an hour. Okay? That's a special kind of stupid. Okay? Nobody in here is that stupid. Okay? But how many of you really go 30? Sure. Okay? Once you have kids, you will. Okay? But most of us don't. Okay? We go, I'll just go 10 over. Because 10's not that much. Right? 10 doesn't make a big difference. I'll go 40 instead of 30. It's not that big a deal. It's only 10 kilometers an hour. Okay. Well, let's just figure out what that'll be in meters per second. Okay, so that's 40 kilometers per hour in meters per second. So I'm just going to punch in the same calculation we had a minute ago. 1500 times now this number squared divided by 7,500. So here's how far I would go if I'm going 40 instead of 30. Our original number was 6.8. So I increase my speed by 25%. Nearly double my stopping distance. Okay? Real world here, guys. Your car is roughly in front of Alec. You're going 30 kilometers an hour, you stop right in front of me. You're going 40, you're past me, through me, and over there, by another 3 meters. Okay? So, should we go 40 or 30? 30, because speed is exponentially related to your energy, and thus the work that would be required to stop you. Okay? It's something to think about. I don't know why they don't teach that in driver's ed, but nobody ever mentions that. Okay? But there's a reason why. School zones, playground zones, and construction zones all have special speed limits. Okay? The likelihood of people popping out in front of their car is much greater in those zones, so you want to be going slower. Okay? And this is all assuming as soon as you saw them, you were able to what? Right? You were actually able to brake. Okay? And your reaction time was perfect.
Wouldn't those numbers change though, depending on like how your brakes like the force?
Oh, absolutely. Yeah, that force, if my brakes are bad or my tires are bald or something like that, that number goes down. Yeah, for sure. This is, I'm assuming perfect conditions, my car's in perfect working order. But yes, those things would definitely affect it. Yeah. Okay, and how big your car is. right? I mean, smaller cars generally have smaller brakes, bigger cars generally have bigger brakes, so brake power is generally fairly equal, but you don't stop a semi-truck in the same distance you stop a Honda Civic, right? It's simple mass, right? Mass is still part of this formula. And the more mass you have, the more energy you have. So yeah, that's something else you have to keep in mind as well. Okay? In fact, for a very long time, there were separate speed limits on Highway 2 for trucks and for cars. There's 110 for cars, but the limit for trucks was 100. Okay? And I mean semi-trucks, so not pickup trucks. All right, is that making some sense? Okay? It's something to think about. I mean, when you start driving, driving's a big responsibility. Okay? And it's a big responsibility because you can't bypass physics. Okay? And driving and stopping and steering and all of that stuff is all related to work energy theorem. It's all related to simple physics. Okay? And so you have to always keep that stuff in mind. That's why you're always told, look 15 seconds ahead. Okay? All of that kind of stuff. There's simple physics reasons for all of that. Okay? Now, as we were saying, this all assumes you react instantly. Are there things that could prevent you from reacting instantly? Like what? Yeah, well, except that most people aren't doing this and looking out the window. They're doing this and driving, which is like really, really bad. Okay? Like it's this bad. Distracted driving makes you more dangerous than drunk. Okay? A drunk person at least will react. I'm not saying that drinking and driving is good by any stretch of the imagination. Okay? A person who's driving drunk has their reactions slowed greatly. Okay? But they at least react. Someone who's on their phone never sees it coming. Okay? Distracted driving is really, really bad, but it's terrible. It's everywhere. Okay? Like I swear every day on my way to school, I see at least 2 people doing it, and I don't have to drive that far. Okay? I see at least 2 people doing it. I've had to like stop and just keep my eyes on, like not looking at other people. Except it's hard not to when they cut you off and really run into the back of you because they're not paying attention. Okay? How much does it affect your reaction time? Lots, actually. Here, I'll show you. Simple demonstration. All right, who's going to be my guinea pig? I'm not going to hit you with it. Right? Colin's going to be my guinea pig? Right. Oh, you can stay at this. Okay. I'll make it easy for you. Okay, I want you to just put your right hand out here, and I'm going to hold the ruler. I just want you to try and catch it. Right, so just like put your fingers over the edge of the desk so you can catch the Oh, sorry. Okay, so I'm going to leave the ruler right in there. Okay, and as soon as you see me drop it, I want you to catch it. Okay, so the ruler fell 36 centimeters. And he was paying attention, right? He was paying attention. Okay, so you got your phone. Now you're going to have to do that left-handed. I realize it's a little weird, but okay? Do I have to watch? Send somebody a snap or something. Just get it on wall. Don't remember your passcode. Oh, and it hit the desk. Okay, that slowed it down. Kellen did pretty well, actually, but it was still 48 centimeters. I've had to do this sometimes when I do this demonstration. I've had people catch it on the rebound. The only thing that told them I dropped it was the sound of it hitting the ground. Okay, I didn't give Kellen enough time to really get into a snap there. Okay, but it still, okay, still affected that. Okay, it fell 10 centimeters further when he was on his phone. Okay, and honestly, that is the best I've ever seen anybody do by a long shot. Most of the time, the ruler hits the ground. Okay, makes a big difference. So when you're driving, take that responsibility seriously.
Yeah,
okay?
so I can drive and look at my phone.
I didn't say that. Your reaction time was dwindled. Okay, like, and remember, it hit the desk. You got the cue of it hitting the desk to tell you, oh, I better close my hand. Right? You got that extra little bit there. Okay? That would have been like the thud of the kid. So, back to this idea of if we go 40. If we go 40, it's still nearly double the distance we would require, right? How much time does going 40 versus 30 save you? Not very much, okay? Let's say you're in a normal playground or school zone. A normal school zone or playground zone might be 400 meters if it's really long, okay? If you're going, okay, if we're just doing this simple calculation, T equals D over V, right, which we've done lots of times. 400 meters at 30 kilometers an hour, that was 8.3. Okay, take me 48 seconds to get through that school zone. If I go 40, I save 12 seconds. And then I get stopped at the same red light as the other person at the end of the school zone anyway. Okay, so just think about this. This is one of those like really harsh things that I'll say to you. If you go 40 through a playground zone, you're telling me and the world that those 12 seconds are more important than me getting to have dinner with my kid that night versus planning their funeral. That's harsh, but it's also reality, okay? 12 seconds. If you are so late that that 12 seconds matters, get out of bed earlier, okay? Driving's a big responsibility. Life lessons today. I'm all about life lessons today. All right, back to physics. Okay, so got this situation here. Okay, this is not a formula we use very much in Science 10, but we use it a lot in Physics 20. Force equals mass times acceleration. Okay, and it's just because this is kind of related to work, force times distance. Okay, if I've got this golfer here and he sets up the way a golfer should to hit a ball, okay, he's going to swing as hard as he can and exert this much force on a very, very small mass. He will produce a very, very large acceleration. Everybody okay with that? Because it's a very small mass. Now, if he does this, instead of hitting a ball, he winds up and smokes this truck. Okay? So he's exerting a really the same force, but now on an incredibly large mass. He's going to produce a very small acceleration. Now, in the perfect physical world, were this truck to be sitting on a perfectly frictionless surface, would it move? Yes. Not very much, but it would. Okay? In the real world, it doesn't move. Does that mean he doesn't do any work?
Maybe snaps the club probably.
Well, yeah, snaps the club, changes the shape of the club, and probably dents the truck. Here's the other thing. As long as any part of the truck moves, that counts as an acceleration. That counts as a change in energy. If I'm standing here at the front of the truck and I have my hand on the hood, do I know when the truck gets hit? Sure I do. Not because I can hear it, but because I can feel it. The vibration will travel through the truck. That means every particle in the truck moves. Okay? They may not move together, but they run into each other and transfer that energy through the truck. To me, I feel it, that's work. Okay? So you don't necessarily have to get an object to move, like actually move, as long as there's some evidence of movement, okay, somewhere in the truck, even vibration. Sound is a form of energy. That's still work. Okay? That kind of stuff. Okay. So motion doesn't, like we were saying here, doesn't just mean the movement of an object from one place to another. If an object is compressed or stretched, the atoms within it are moved. Vibration, atoms are moved. Okay? Thus, the changes in the shape of an object constitute an exertion of force and will result in work and energy transfers. Okay? So that has to do mostly with elastic objects. Okay? Stretching a rubber band or bungee cord, okay? Or something along those lines. All right, now, first day of this unit, we talked about work and heat. Okay? Work and heat are both transfers of energy. Okay? Work is a change in mechanical energy. Okay? That's potential and kinetic. Okay? Heat is a change in thermal energy. hot to cold. Okay, transferring thermal energy to something else. So they're both transfers of energy, they just transfer different kinds of energy. We're worried about this. Okay? Now, mechanical energy obviously can turn into thermal energy. Okay? Friction would cause that. But we're mostly working here with changes in mechanical energy. So either a change in height or a change in speed of an object. Okay? Now, I keep saying speed. I think I've said velocity a couple of times, but I mean speed when I'm talking about energy. Because energy, vector or scalar? Scalar. Energy is a scalar quantity. Energy does not have direction. It is your ability to do work. That doesn't have a direction. Okay? If I eat like a supersized Big Mac meal, okay, I don't say that I consumed 5,000 joules of energy north. It's going south. It doesn't have a direction. I now have 5,000 joules worth of energy to do with as I choose. Probably convert to fat, but okay. I might use it to do work. Maybe I'm going to go and run and then keep it all up. I don't know. Okay, but I'm going to use the energy that's in it, okay, to do something else. So energy is scalar. Work is scalar. Okay, work is also a scalar quantity. I might transfer energy to something else, but again, it's energy. Energy is scalar. It doesn't imply direction. Now, that said, work is scalar, but work can be positive or negative. Does that seem contradictory? Yeah, it should seem contradictory, okay? Because positive and negative implies direction. And in this case, it sort of does, but sort of doesn't. Okay? Work can be positive or negative depending on whether you're doing the work. That would be negative because you'd be transferring energy away, or having the work done to you. That would be receiving the energy. That would be positive. Right? So work can be positive or negative depending on whether you're transferring energy away or having it transferred to you. Okay? So it isn't about direction. It's just about whether you're gaining or losing it. Okay, so potential energy we'll talk about first. So potential energy is energy due to position or condition. We talked about that before. We're going to be looking at strictly gravitational potential energy. Okay, so we had Wile E. Coyote this morning on the quiz. Okay, so let's say both Wile E. Coyote and the anvil are both falling. We're looking up, seeing these two things are falling down towards us. Which one would hurt us more? The anvil. Why? It weighs more, right? It has more mass. Okay, mass is part of energy. Okay, potential energy is calculated by taking the mass of an object, multiplying it by the acceleration due to gravity, which for us is 9.81 meters per second squared. And what else might affect how much potential energy you have?
Air resistance.
It won't affect your potential. It could affect the kinetic that you get as a result. How far it is from the ground, or height. Okay, this here, that's our formula for potential energy. Potential energy is affected by an object's mass. Okay, that's why you immediately recognize the anvil would have more energy. Okay, acceleration due to gravity, they're both falling on Earth, so that's the same for both of them, and the height from which they fall. So, is it possible for Wile E. Coyote to have the same amount of potential energy as the anvil? He would just have to be way higher, yeah, okay, like way higher, okay, than the anvil would, right? Then they could both have the same amount of gravitational potential energy. Okay, so if I take an anvil on Earth 10 meters above the ground, it'll have a certain amount of potential energy. If I take it to the moon and put it 10 meters above the ground, does it have the same amount of potential energy?
No.
Why not? Gravity is less. Yeah. Gravity on the moon is 1/6 of what it is here on Earth, so you would have 1/6 the amount of potential energy. So you can actually fall further on the moon and not get hurt, because you won't have as much energy when you fall. All right, so gravitational potential energy is the potential energy of an object due to its position, okay? All forms of potential energy are described with respect to a chosen reference point or condition. That chosen reference point is usually ground level. Usually, isn't always, but usually is ground level. All right. In the picture on the left there, okay, the two people with the blocks, okay? Who is going to do more work in getting the block to the top of that ramp? The person who lifts it or the person who pushes it up the ramp, assuming the ramp is frictionless? Okay. That's usually what people say, because they recognize that it'd be much harder to lift the rock. Okay? But how hard it is to lift the rock isn't about the amount of work. It's about the amount of force that you would have to exert. Okay? Remember that work is a change in energy. When this thing gets to the top of the ramp, regardless of whether it was lifted there or pushed there, its potential energy has changed by the same amount. Okay? We just looked at that potential energy is mass times gravity times height. Either one of these blocks are identical. They get to the top of this ramp, they're the same height off the ground, which means they have the same amount of potential energy. So, lifting it and pushing it up the ramp are the same amount of work. But what's different is how hard that work is. To do this, I have to exert a greater force because it's a shorter distance. That's the purpose of an inclined plane. An inclined plane makes work easier. I don't have to exert as much force to push something up a ramp, but I have to do it over a greater distance. Right? That's why the inclined plane is the simplest machine. Okay? It makes work easier. It doesn't make less work. Right?
Sorry, but I have to say it like has to do with like what we're talking about, like not physics necessarily. Like I've been reading on the pyramids, and they're saying that like they think alien technology built them because they have like 500-ton platforms and they can't pull them up like the girl in the red suit.
Mm-hmm.
So like I was wondering, like, do you think that would be physically possible to get a bunch of men to be able to pull up like 5-ton beams up a giant slope? I don't know.
Absolutely. Yes, because what I've seen on the building of the pyramids, because I fell down that rabbit hole myself, okay, was that when they were building the pyramids, they actually built ramps that went around and around and around, not spiral, but like blocky, okay, and going and going on. So those ramps, by the time they were getting to the top, were like kilometers long.
Okay.
Right? So there wasn't a big incline. And back when the pyramids were built, Egypt looked a lot different. Like that part of the Nile would have had more like trees and stuff.
Yeah.
So they would have had logs. Put the blocks on the logs, roll them along the logs, move the log to the front, keep rolling it. Like it would have been much easier than dragging it through the sand, right? To get it to the top.
Yeah.
You're right. They would have had no way to lift it to the top because that's a huge amount of force for those blocks, right? They were huge. But to move it up an inclined plane like that wouldn't have been as difficult.
Yeah, that makes sense. The one I was reading, the guy was like, yeah, they were like attaching strings to it, like trying to pull it up like the giant staircase thing there. I was like,
Yeah, no, they wouldn't have used any of those internal structures, no.
oh.
Yeah. There was also some stuff that said because the insides were hollow, they could have had like a offsetting kind of sand lifter, so as sand would go from one side to the other and it would like pile in. I don't know, it was some weird thing, but yeah, the inclined plane one seemed to make the most sense.
Yeah.
And when they started diagramming how that would have worked all the way around, and then they just moved the sand away at the end, and poof, there's the pyramid. I mean, they had lots of sand, lots of slaves. You can get a lot done with sand and slaves, apparently. So, all right. So does this part make sense here? Okay, about the amount of work. Okay, this is kind of that lesson on work's a change in energy. Okay, getting this thing to the top is the same amount of work regardless of how I do it. Okay, I change the energy by the same amount. All right. Okay, so that was the formula we were just talking about. So EP is gravitational potential energy. Units for energy are joules. Okay. M is the object's mass. In physics, we always use kilograms. Chemistry always uses grams. Physics always uses kilograms. Okay, so the mass of everything in this unit will need to be in kilograms when you put it into your formulas. G is the acceleration due to gravity. On Earth, that's 9.81 meters per second squared, unless you're told otherwise. Okay, and H is the object's height above the ground in meters. All right, so that formula is going to be pretty easy to use. Yeah, because everything's all in a row, right? If I need to manipulate this, I just divide off whatever else, whatever I don't want to leave. So if I'm solving for M, I divide both sides by GH. If I'm solving for H, I divide both sides by MG. Okay, it's super easy to manipulate, and there's nothing really complex or tricky about the math. All right, so let's look at a simple example, then we'll call it a day here. So 3 kilogram box is lifted by an upward force 1.5 meters above the surface of the Earth to the top of a table. What's the potential energy of the box in its new position? All right, so we know the mass, okay, we know the height, and they told us it's Earth. So what else do we know? We know gravity. Okay, so all we have to do is go EP equals M times G times H, 3 kilograms times 9.81 meters per second squared times 1.5 meters will give us 44.1 kilogram meters squared per second squared. That's a joule. Okay, you're not going to need to know the base units, but that's what we get. In case you were looking at the units in that question and going, how does that give me joules? Okay, a joule is a kilogram meters squared per second squared. All right. Can potential energy do work? Nope, it can't. It has the potential to do work, hence the name. Okay? But something sitting on a table has the potential to do something. It isn't actually able to do it until that potential energy is turned into kinetic energy. All right, we'll leave it there for today. You guys can clear off your desks. I'll come around and spray them down. Thank you.